All right. So I want to start by asking you guys some questions. As I know this is like a developer conference, everyone here is Java centric, and this is a talk about things in the MLAI space. So, kind of my first question for you guys is, how many people here the first time they interacted with some sort of like AI system was like November of 2022 when it was ChatGPT? It was your first time. Never done it before. Okay. How many people here have like built a or trained a machine learning model or like deployed it themselves? Okay. Oh, okay, cool. And then I guess for the context of the talk, how many people here have run a local large language model themselves? Just run one. You pulled it from somewhere and you ran it. Okay. Cool. All right. So maybe this audience will find this talk enjoyable then. So yeah, this talk is titled "How to Build a GPT for All." So GPT for All is kind of a colloquial term that I'm going to be using for when I talk about a local large language model. A large language model that you can run yourself. A large language model that you can use without having to send all your data to a third-party service running on American servers and hoping that they don't use your data to do something that you don't want them to do. So the basic outline for this talk, I'll talk about the history of LLMs. So LLMs have a rich history. In general, the field of deep learning has a rich history before November of 2022, and most people don't know about it. So I'll give a brief intro into that. It'll be a terrible intro for anyone who's a researcher in the space. They'll find it incomplete. They'll find it boring, but I think it'll be interesting. And then I'll talk about how we can make these models, these gigantic large language models that take tons of compute to train, run on low resource devices that are kind of akin to toasters. If your toasters have 4 to 6 gigabytes of RAM, and we'll go into sort of the data that we need to put into these models to make them actually act like these chat assistants you see from OpenAI, what these models look like, how they work a little bit, and sort of the tips and tricks you need to be able to do to these models and why those tips and tricks work to be able to make the models run on devices like these laptops. Yeah, and then we'll do these sort of like grand hurrah. It's like, okay, these models are great. Anyone here in this room who raised their hand to say like, oh, I've used these local LLMs, you'll find that they're much worse than what you get with like ChatGPT. And I'll talk a little bit about like where we need to be and sort of the next steps that the world's going to take to be able to reach these sort of like GPT-4 ChatGPT quality models, but being able to run on your local servers or even like your local devices. So to kind of start out the old brief history lesson, I'm going to start it basically in 2017, which is going to ignore the past 30 years before that of work that got us to like where 2017 put us. And this is this paper that came out of a group of folks from Toronto and Google called the Transformers paper. The attention is all you need. So the Transformer was this deep learning architecture that sort of revolutionized how computers can interact with human language. Before that, it was very, very difficult to make computers be able to do something reasonable with human language. Things in the image space worked really well. In text, it was just hard. The previous systems just weren't general purpose. And so these group of authors basically were out trying to basically improve machine translation systems, and they stumbled across this deep learning architecture, which relied on this idea of self-attention, which is this like deep learning operation, which turns out is super crucial to pretty much every single major advance you've seen in the last 4 years. Everything you've seen in the image generation space, everything you've seen in the video generation space, the audio generation space, obviously the text generation space, it's all based upon the ideas that came out of this paper. So all these academics, some of them are working in academic labs, some of them are working in labs in industry. What did they do once they realized that they literally just invented the thing that's going to transform how humans interact with machines? Well, they all left and started their own companies. So Ashish Vaswani went to go start Adept. Adept was this company geared around creating sort of an AI assistant for your browser. As you interact with your web browser, it learns the actions, and then you can just type in a piece of text, and it can go perform a browser flow for you. Noam Shazir went to go found Character AI. I'm sure many people in this room have probably used Character AI before. It's sort of like the most user-facing LLM application that is in ChatGPT. It's the easiest way to sort of like create your own local characters and have your like AI friends to talk to. Both of these companies are valued at billions of dollars. Aiden went to go start Cohere, which is a large language model foundation company that's valued at a few $billions. So as you can see here, these authors back in 2017 saw the impact of what they had invented, but it took about 4 years for sort of this stuff to kind of come to fruition and be at the point where in November of 2022 you can interact with a model like ChatGPT through your web browser. So this is sort of like showing some of the lineage. So a lot of these groups went through from this original paper and these original groups in Google. They went out and there were tons of companies started basically leveraging this technology for sort of applied applications. Some of the more notable ones that I didn't mention in the previous slide. So Anthropic spins out of OpenAI. OpenAI was sort of the first the first organization that went in and scaled transformers up. This is why they had this sort of early start, which enables them to have models like GPT-4 right now. Perplexity AI as well. There's lots of co-founders of that company, but Perplexity is another organization that's making this sort of like a universal search engine, basically trying to kill Google. Basically, this is all to say is that in 2017 there was this revolutionary moment when people realized that you can achieve very powerful generative systems just by scaling up data and just by scaling up the size of your machine learning models, and you don't have to do a bunch of fancy math. You don't have to be a mathematician to be able to create a powerful machine learning model. And that's the game people started playing. So what happened is over the years, ever since the Transformers paper was published in 2017, people were looking at, okay, what can we do with the capabilities of these models? Originally, these were models that were based on text generation. These are all these green and red and blue squares you see on this page. And as you can see here, the very sort of first powerful generative model that came out was the GPT-2 and GPT and GPT-2 models out of OpenAI. These models are actually open sourced. OpenAI used to open source their models. They didn't just hold them behind closed doors. You had the generation of transformer encoders out of Google. So Google, they were the ones who invented this deep learning architecture, and they actually were also the ones the first to productionize it. Google Search was running a large language model behind it back in like 2020. And over time, one of the most interesting things that happened is what people realize is that as you scale these models, so this y-axis is logarithmic on the number of parameters. So a parameter is a floating point 16 or floating point 32 number, and that 10 billion means there's 10 billion of those in the model. Over time, they scaled, and they scaled exponentially. So every single year, the sort of average size of the best-in-class generative AI model that existed, foundational model that existed, was increasing exponentially. And what sort of happened here is there was this really interesting point in about 2021 and 2022 where a lot of big organizations realized, wow, they had built something that you can actually make a product out of. And that was about the point where people stopped open sourcing actual access to these models. So DALL-E was one of these first, GPT-3 and DALL-E out of OpenAI was one of the first sets of models that OpenAI refused to open source. They did not actually give out the weights to the model. They only gave API access to the model. And that's many organizations past that use that as an example as to like the status quo of how a machine learning model should be released. And one thing I also want to note here is that like there's things that aren't text generation systems here. There's image generation systems. There's audio generation models here as well. So basically, the idea here is transformers. That's the architecture that dominates the generative AI space. The models get really big. When the models get really big, what happens is they get really expensive to train. And the reason there's arguable reasons for why you want to keep these models closed source. The investment to actually create one of these large models, these models towards this 100 billion, 10 billion parameter range, they cost hardware that costs you on the order of like 10 to 20 to 30 million dollars to build up a cluster. So this machine that you're looking at right here, this is a sort of NVIDIA's box of 8 GPUs. They call it a DGX. The GPUs that usually go in here for large language model training are called A100s or H100s. One of these boxes right now, if I was to call up NVIDIA right now and be like, hey NVIDIA, I'd like to buy an H100 box because I want to train my fancy new large language model. They'd be like, all right, great, that'll be $500,000 and you can get it in 1 year, but you have to pay us now. So that's the state of the world right now. And in order to train one of these actual foundation models, these 100 billion parameter models, you don't just need one box. Oh no, you need 256 of them, all linked together with super fast interconnects that you actually can't also get right now. So as you can see here, you have this sort of like, this incumbent advantage forming in this whole AI space. Companies that realized that scaling compute and scaling data was important in 2018, 2019, were able to buy tons of GPUs like Google, Amazon, Meta. They're the ones who actually have access to the compute to train these models. So the models that they produce, if they don't open source them, nobody can get a model as powerful as this. So that's one point. And what happened here is that they went industry. They went the direction of commercialization. They realized they were the only ones who can train these models. They knew no one else could get the compute. And then you had organizations like OpenAI, Anthropic, Cohere, turning these big models into a company. They became services. They're serving you embeddings through their API. They're serving you text generations out of the API. And basically what happens is this really screws over researchers. All of the work that these organizations have built upon was work produced out of research labs, sometimes funded by some of these organizations, but oftentimes not. And now it got to a point where, in order to improve the sort of state-of-the-art systems for doing text generation, for going through and doing the most powerful AI operations over top of data, you had to go through the APIs of these companies. So that was pretty much the state of the world up until January of 2023. As many of you raised your hands and you saw, that's not quite the state of the world right now. And the rest of this talk is going to be exploring that. But maybe I'll talk about some issues first around centralization. So essentially, what happens when the only way to access the most powerful AI systems is through the APIs of a few large companies? Well, basically all the things you can imagine would happen when you have one organization controlling basically the most important technology that's come to be in the past 10 years. A technology that transforms how everyday people can interact with computers. You no longer need to be a programmer to be able to tell a computer what to do. You can use natural language to do it. So for example, lots of industries just couldn't even access the technology, period, because of various. I'm sure many of you here, you can't actually access ChatGPT or GPT-4 in your work environment. Your boss just says no, like we're not going to send our data over. Samsung had a really good case back in last March, where their chip designers were actually iterating on their chip specs and were pasting it into ChatGPT. And what happened is, turns out at that time, OpenAI was taking all that data, training on it, and then pushing out the next model. So these billion-dollar chip designs actually were then spit out of the model, the next generation of the model. So if I went and stole chip designs from Samsung, right, I'd get sued into oblivion. If I send my data to some third-party company servers with a terms of service that's a little bit flawed, or to whatever specification they set it, they get a slap on the wrist. Essentially, there's large problems when the most powerful technology is not held by is held by a few organizations. And this is, so my background, I came from the research world. I was a PhD student at NYU prior to doing what I'm doing now. And so the thing that really irked me with all of this was the fact that they were sort of going against what their original thesis was. The original thesis of OpenAI was, we want to build powerful, open artificial intelligence such that we can minimize the worst case scenario of what happens, when you have an AI system that can go and do things that even a human wouldn't even be able to do. And they found that sort of like the safest way of doing that was to go in and hide everything that they were producing. So this is actually a line from the GPT-4 white paper. It's not a paper. It's basically a brag session. And sorry if this comes off of me berating OpenAI, but like this is the part that I really this is really irked me in March. Given both the competitive landscape and safety implications of large models like GPT-4, we're not going to tell you anything about the model. We're not going to tell you anything about how we trained it. We're not going to tell you how much money we put into it. We're not going to tell you what data went into it, the sort of licensing of the data, none of that information, anything, period. You can speculate. People have speculated. A lot of people have the recipe. There's people chat at bars in Silicon Valley afterwards. People have some idea how this model works. But they went completely sort of 180 on their original thesis. They were a nonprofit funded for essentially AI safety back in 2016, 2017, and now they went the whole commercialization route. This pissed off many academics. So that's what basically the state of the world in March of 2023. So how do we not live in this world? The question is, how do we not have to use the most powerful AI systems without having to do this? Well, the answer to that is simple. There's basically a recipe that you can use to train your own model, and for many tasks that you might care about, for example, not everything in your business might be, being a general purpose chatbot that's able to do both translation and story writing and question answering all at once. For specific tasks, you can get local large language models or large language models that run on your servers on cloud services that actually are pretty competitive with GPT-4 and ChatGPT. So the rest of this talk, we'll talk about how to make one. But before that, I'll tell you who I am. So I'm Andriy. I'm the co-founder of a company called Nomic. We're a startup based out of Flatiron, New York. Basically, what we do is we build accessible and interpretable AI systems. So we focus on what does it mean to make an interpretable AI system? What does it mean to put the best data into your AI system? We build tooling around improving data quality and the interaction of unstructured data. And also, we maintain one of the largest GitHub repositories, the third fastest growing GitHub repository in GitHub history, actually, allowing anyone to run local large language models on any device they have. And that's what this talk's about. It's about GPT4All, how you can go about running these models, how you can go about making them. And here I'll jump into the details of what you need to actually go and run them on consumer grade CPUs, what the tech stack sort of looks like, and sort of like the considerations you want to have along the way. But before I do that, let me just show you one of these things running. So this is a chat application. It's built over top of the GPT4All C++ backend. And it basically allows you to download any local large language model that you see out there and run it. So let me actually make this a little larger for everyone. So write me a story about giving a talk at Devox, Belgium. So this is a 3 billion parameter large language model that has been trained as a chat assistant. So it's been trained on examples of back and forth chats between a human and a large language model, so ChatGPT or GPT-4. And what it does is it's able to go through and replicate basically the behavior while taking the parameters that it was originally pre-trained on those big collections of GPUs and incorporate that knowledge into the chat session. So I can say, what about the Belgian beers? And you'll see you can go in and continue the chatting. Write me a structured JSON categorizing Belgian beers. And maybe it'll generate a structured JSON. Oh, there we go. Chimay. I haven't tried that one yet. I don't know. I've really enjoyed the Belgian beers the last few days. But basically, this is what you're able to run. All of this is running on my local MacBook, by the way. Maybe I should have turned off the internet to demonstrate that to you. But the principle here is you can do this yourself. And if you have a business, your business can run it themselves too. So how do you build one? First, you want to start out with the model. So as I was showing you in those big graphics with the logarithmic axes about the models getting larger and larger, the secret is you want to start out with the transformer. So do what all those guys did in that first slide that I have. Leverage all the work that they put in. And it turns out if you want to build good generative models, you want to go down the route that OpenAI did. So OpenAI were the first ones that introduced a transformers model that was decoder only. So they trained it. So traditionally, a transformer model has an encoder section and a decoder section. When you interact with a model like BERT, you're usually working with the encoder. So the decoder only models allow you to go in and perform generative modeling. There's a few sort of reasons for that. I'm not going to get into this talk, but oftentimes, there's a few good talks at this conference as well on like legal text and fine-tuning BERT. For domain-specific tasks, you should probably go do that. You don't want to be going through and using a generative model to create a class label for you and this sort of thing. There's better methods of doing this. But if you care about going through and doing text generation, whatever that text generation would be, you want to use a transformer. And that's what we do in GPT4All. So GPT4All, it's an ecosystem of 6 billion to 13 billion parameter models. This is about and I'll get into the details why, this is about the parameter range where you get this sort of nice trade-off between being able to run locally on CPU and also being able to get models that are like of the quality to be able to do things like I was just demoing to you. And most importantly, these models are based on open core backends. So the actual core foundation models that the recipes inside of GPT4All and sort of the bindings for fast CPU inference support are based around inference on models like GPTJ, Llama 2, Falcon, and MPT. So these models are models that are actually Apache 2 licensed, which means like if you go in and modify those models in some way, you can go in and run them yourself in like your business, and then Meta can't go and give you a slap on the wrist and take away all your hard-earned money. And so it's really based around this thesis like you should be able to own the models that you're building. The next one is the kind of data that goes into them. So what kind of data do I want to throw into a large language model to actually make it be high quality? And this is sort of a difficult question. First of all, it's like, how do you get this data? Second of all, what does the data look like? How much do I need to spend to train my model on that data? And also, how do I curate that data set to make it high quality? So what I'm going to show you here is a data explorer which allows you to actually see the training data set of this GPT-J model. It was the first Apache 2 license model that was released. We're actually the ones who trained it. Ever since then, there's been many more models released. They're of a lot higher quality than the ones that we were releasing back in April and March. Rather, March, April, and May. But this sort of like gives you a view into the training data. So like every single point that you see here on this data explorer is a data point that was used in the training data set of this model. And 2 points are close together if they're semantically similar. So this interface allows you to very quickly find sort of erroneous data points or duplicate data points that you might want to remove from your data set. But like to give you an example here, here's questions coming from Stack Overflow, and the responses here are actually coming to, this is a data set used to train the smaller model on. The responses here are actually coming from a larger model. This is specifically here ChatGPT. So the sort of secret that everyone goes around and that everyone uses is that you can actually use this machine learning technique called distillation, which means you take a larger model and you distill its outputs into a smaller model without having to go through the laborious process of collecting like high quality annotated data out. So what you can literally do is create a bunch of questions. Questions that a human might, for instance, ask. And the model will learn, based on the questions, the kind of style of responses you want it to give it. And the smaller model will mimic the larger model. So the goal here is not to actually like instill knowledge into the smaller model. It's to sort of guide it in the way it's able to go in and generate such that it feels like a chat model. It feels like something that humans will accept. And sort of the styles of questions that went into our original model were everything from the range of poetry to writing sort of like plays and writing stories. I'm not going to dive into this too much. You can go explore this yourself. But this is sort of this is just a nice viewer to be able to quickly explore that sort of unstructured data. Jumping back here, how do I full screen this? Okay. So yeah, data quality is important. Making sure your data is deduplicated is important. I'm actually going to hit on this again later. The data quality is the most important step. Most data sets, if you go on Hugging Face and you go in and try to train your own model, I wouldn't recommend actually using this data set. It's quite outdated. There's other data sets like OpenOrca out there that I would recommend using. They actually used this tool as well for curating the data for that data set. But most important things are making sure your data is highly deduplicated, making sure that you have gone in and sort of sampled the space of possible interactions your end user might have with your model. And if it's very, very much domain specific, so you're building a model, for instance, like for legal question answering, you have questions coming in from that domain. But this is sort of a general purpose chat model. It was very, very much served as like a proof of concept demo back in April. Hence, you have this sort of like sets of questions that maybe a general user might ask when they land on a machine learning model. And how do you actually train this thing? Well, it turns out in order to train the actual foundation model, in order to train a Llama 2, in order to train a Mistral, in order to train a GPT-J from scratch, you need those, 64 DGX A100s that you have to go rent for $24 an hour per box from some cloud provider. But if you actually want to fine-tune that model so that you have the initial set of parameters baked into that model that teaches the model a lot about language, to actually fine-tune it to be a chat assistant model, you don't actually need that much money. So this is actually an over-exaggeration of how much money you need. You need actually way less now. There's been a lot of like low parameter efficient fine-tuning techniques that have been released. But back in April, we went through and sort of like as one of the first seed models into this local model running repository for $200, we were able to rent a machine and train over top of these 1 million data points that we had gone in and curated for LLM training. So it's actually surprising. Most people assume like it's super expensive to be able to replicate something that previously you can only access over API endpoints, but you can get a super high quality model for pretty low cost relative to like its capabilities nowadays. So you grab a you grab a GPU machine, you grab an off the shelf script off of Hugging Face or anywhere else, and you can get yourself a set of parameters that is sort of like biased in whatever way you want. And then this is sort of like the most important part, I would say. This is the part of actually getting it to run locally. So when you have a language model that has like 7 billion parameters, I assume it's like in 16-bit precision, you have about 23 gigabytes worth of weights. This MacBook is 16 gigabytes, and it's considered sort of like a high-end MacBook. Most everyday consumer devices or edge devices, you won't actually even be able to fit that model into memory, let alone inference it without swapping and going and just because things becoming super slow. But it turns out that there's this really interesting thing that you can do, and next slide I'll talk about why it actually works. It'll be a nice little graph. But there's a really interesting thing you can do called quantization. So what this means is essentially you could bin the parameters of the model. So for every single like subset of parameters, for a fixed subset of parameters, you can bin those parameters by looking at the statistics of the parameters to being not taking up like 2 to the 16th possible values, but taking up, for example, 2 to the 4th possible values or 2 to the 8th possible values. So you're quantizing it to a lower set of possible floating point values. And in doing this, you can represent it in a format that by doing this, you can go in and represent the model weights in a format that is much less intensive for like bandwidth transfers when you're doing inference. What this means is that the models can run faster, and they can also actually fit in the RAM of a low resource device. But actually, one of the most important things is the fact that you just have less model weights to move around, and what that means is that you don't have to eat the memory transfer costs of actually that come with doing inference. And this is why it works. So this is like sort of a surprising thing, right? So I have a 7 billion parameter neural network, and I go in and I just take every single weight and I reduce it to one of 16 possible values, and it still runs well. That makes no sense. Why does that actually work? Well, it's actually an empirical property that people observed. So OPT, it's this model that out of Meta, it came out before Llama, and this is actually a clip art, a screenshot from their paper. So the lines here, the way you read this is the x-axis is the size of the model, and then the y-axis is this metric called perplexity, and lower is better. So the lower perplexity that you have, the higher quality the large language model is. And each of these lines that you see here is, so a single point is a model, and the lines sort of trace the perplexity at a given quantization. So floating point 16 is the usual quantization a large language model gets run in. And the interesting thing to observe here is that there's a very, very big gap when the model is about 1 billion parameters. There's a very, very big gap in the perplexity, and like this might not look like a big amount, but like if you go in and actually use the model, you'll see that it's trash. Like it's nothing that you would it's nothing you would ever want to use for any sort of purpose. But at about the 6 to 7 billion parameter range, it turns out empirically, most of the information that's contained in the model can actually be constrained into those 4 bits per parameter without losing the perplexity. So this graph is sort of like this graph is the reason you're able to even run local large language models. At about the 6 to 7 billion parameter range and upwards, the actual end error after quantization gets nearly to the same error that you have when running in floating point 16. And this is just like an empirical fact. People were able to observe this across sort of model types, and this is like why you even get projects like Llama CPP being even possible, for example. Yeah, so this is just super fascinating. Like when I found this, it seems like it should make sense. But it is the case that in order to train a neural network, you need to be in high precision to make the training dynamics work. But it turns out most of the information in those end trained weights aren't actually needed for the high quality sort of behavior that you want at inference time. So you can go in and quantize it down. So there's that. And to kind of egg on this a little bit more, as I think this is really the most important part. This is the part that people don't realize. Like it feels stupid that you should be able to delete, almost all the information out of your weights, and the model is still as good as it is. The reason it works is because the whole goal behind quantization is for the same input in floating point 16, you want to preserve the floating point 16 output. And so basically you solve an optimization problem. So this is just a linear optimization problem where you have the weights in low precision, you have your floating point 16 inputs and outputs, and the whole goal is to make sure that the inputs and outputs in floating point 16 match the inputs and outputs in int4 precision, for example. This is it's actually as simple as this. If you've taken an optimization course, like it's not a complicated algorithm to run. But yeah, so quantization. This is why you can actually fit them on devices this small. And so what is GPT4All at the end of it? It's basically all these things put together. You have the models, you have the inference code to be able to run them, you have these sort of like empirical observations about running large language models of various sizes and what you can do with them when you quantize the weights down. So what we have here, GPT4All under the hood, what it is, it's a fork of Llama CPP. Llama CPP is this repository where it implements quantized tensor operations that allow you to run the operations that go into doing a run of the neural network, but running it on CPU. And then we built sort of like we built a suite of decoding algorithms and also a suite of tools to make it more accessible for everyday people to use. So the reason people even care about this repository is we were sort of the first people to actually go in and make the model super accessible to people. It used to be the fact that you had to know C++ and C to be able to even use this tech back in March. We were the ones who dropped the GUI over top of it and also actually trained the models that actually felt like good chat assistants that were Apache 2 backboned. And what it allows you to do basically is to go in and run 7 billion parameter models pretty fast on your machine. So what I was showing you here at inference time was actually a model running in on Mac Metal. So there's if you have sort of like better hardware devices, we have kernels built in that optimize for like M1 and M2 chips on MacBooks. But what we really design it to be is sort of the easiest place where you can go in and get started running a large language model as fast as it possibly can be on your hardware that you have. If you have a Raspberry Pi, great, it'll work. It'll be slower. If you have a MacBook, great, it'll auto detect that and use the appropriate kernels. The biggest thing is also Apache 2 licensed. So the goal here is that you should be able to build a large language model yourself, and you should be able to run it without worries that somebody's going to come and sue you. You should be able to run it privately. The data should all stay on your machine. Yeah. And one of the cool things is that our company, it's a startup. We make money. That's like the kind of whole idea. We have this open source arm now, which has been really exciting to sort of participate in, where we have a growing developer community of C++ engineers, people who have written Python, JavaScript, and Java bindings. So you can actually run this in Java if you wanted to, and even like Docker-based images to be able to run these models on Kubernetes clusters. So there's like a growing open source ecosystem around this project, and yeah. And so one of the newest things, this is actually what I wanted to hit on at the end here, is we've actually gotten the ability to run accelerated GPU inference on a variety of GPU types that aren't just NVIDIA. So usually when somebody goes in and implements GPU inference for some sort of like neural network library, what happens is that you can only run it probably on NVIDIA GPUs because nobody can ever write good enough software to be able to do anything useful on any other GPU. This is the usual thing in machine learning. So we spend a bunch of time and let an open source effort to basically enable GPU inference across a variety of GPUs. So if you have a Qualcomm GPU plugged into your machine, an integrated Intel graphics CPU, integrated graphics GPU or an AMD GPU, if that exists in your machine, the library will actually automatically leverage it and utilize the appropriate custom-written fast kernels to be able to perform LLM inference over top of it. And what we did this, we actually built over an open standard. So how many here have ever heard of Vulkan? Hell yeah, cool. I don't get that same response on the East Coast. Vulkan is basically the successor to OpenCL. It allows you to implement arbitrary operations lets you implement arbitrary operations for running on GPUs, and it compiles down into sort of like the target languages that for each GPU. So if you have an NVIDIA, there's a driver for ROCm that works with Vulkan. And what we did here is we spent a bunch of time. This was actually an internal effort at the company. We had some open source participators in it, but turns out if you want to write a bunch of kernels, people don't enjoy doing that. But we get them in there. They're open source. You can go in and basically run any foundation model you have out there through the GPT4All stack against Vulkan. And what this really means is this kind of goes in the direction of accessibility. We shouldn't live in a world where the only way to access this technology is if you have a lot of money to be able to buy expensive graphics cards. You shouldn't be able to only be able to access this technology if you have to go through the servers of OpenAI or Anthropic. You should really be able to run it anywhere. And that's the general mission of the project. We want to make sure that the most powerful generative AI systems can be run on the sort of smallest, cheapest machines. And this is sort of showing you some benchmarks. This is basically our flag planting that we did it. So we actually beat OpenCL in this implementation. So this top line here is the actual backend. This is comparing different model sizes: 3 billion parameter, 7 billion parameter, 13 billion parameter models. And as you can see here, they go very, very fast. It works with NVIDIA GPUs. It works with AMD GPUs. So basically, any GPU you have plugged into your machine, you can get an LLM running pretty fast on it if you use this stack. We're actually working on upstreaming it into upstream Llama CPP as well. Yeah. And yeah, if you want to use it in code as well, it's not just like a chat client. You can go in, write it in Java, write it in Python. It's literally this easy. You pick in your model, you just say GPU, and it'll pick the best one. So it's really one of the easiest ways to get started. And then when it comes to models, at the beginning it was us and like one or two other organizations who were working on actually training these open source chat assistant models. Thankfully, people have realized this is a thing that's actually quite easy. As I just showed you, it's not that hard. There's a few steps, and if you want to go in and find recipes online, there's like tons of examples where you can go in and train your own models. The data sets are all open source. That's kind of one of the biggest things, actually. The data sets are open source. The hardest thing is getting the data for these things. This is the competitive advantage that OpenAI and Anthropic have. They've done the best job at curating high quality data sets to actually train their models. This is why GPT-4 ChatGPT is so much better than any other open source model. They just have much high quality data. They paid Scale AI millions of dollars to collect these high quality input-output sets for training the models. But you can go online on Hugging Face right now, pull in any of these models that you see, and they'll all work. They're all variants, different flavors. One of the coolest things about local LLMs is that you can go in and sort of like bake in your own bias into the model. With OpenAI's models or Anthropic's models, what happens is like you want to use that LLM, great. You want to use it for business purposes, you probably can. But what happens is if you want to use it for any purpose that doesn't align with the belief structure of a group of people in Silicon Valley, likely the model will tell you as an AI language model, I can't do anything. With these local models, you don't get that. You can bake in whatever bias you want. And that's pretty cool. People should be able to have control over the systems that are running on their machines. People should be able to, ask their machine learning model, how to kill a Docker process and not be told, killing is bad, right? And that's a famous example from Meta's Llama 2 model. Yeah, so the thing I want to hit on again is like data quality is key. It's super important if you want to fine tune your own model that you have a good data mix. If you spend your time on anything, spend 95% of your time looking at your data set, working with your data set, improving it, making sure that the data points in your data set are representative of like the kinds of use cases your model will have downstream. And then 5% of your time actually like doing any engineering to like build the actual end model. It's that important. The bad data will screw up will screw up your whole mix. And kind of some of the things that we focus on specifically are prompt diversity, so making sure you cover the range of possible use cases you have at the end, ensuring output cleanliness. So a lot of times you'll have sort of like malformed characters and this sort of thing in the data that you're training on. You don't want to do that, and also heavy deduplication. LLMs are amazing at memorizing things. If you have duplicates in your training data set, you will find that your model really likes to output certain types of phrases or themes. And not other ones, just because you had a couple of extra upsampled examples of like one specific question type or one specific mode. So duplication is really important. So where are we going with this? We're going in a few directions. One of the biggest directions is accessibility across the entire development stack. So as I mentioned, now we have bindings across every sort of major language to our C++ API. We have Docker images you can run on Kubernetes, which is all fun. One of the other things is that we have some internal research projects happening in Nomic that we'll be open sourcing the next few months, where we actually give these models access to multimodality. So if you've seen recently ChatGPT dropped multimodal capabilities, you'll be seeing quite similar stuff appearing in the open source world pretty soon. And it'll all be able to run locally on your toasters. So that's pretty exciting. And yeah, so the very last thing I promised to you is like, great, we have these local LLMs, you could run them anywhere, it's a really cool demo at a hackathon, but like, how do we actually make them useful enough to deploy in an industry setting? What do I actually need to do to be able to get a model as general purpose, high quality as like a ChatGPT? Where does the open source community need to go? Well, the first one is you want to train on a lot more data. Usually the training mixes, and actually this is, since I made this second slide, this has actually been done. I'll get to that in a second. But training on a lot of high quality tokens, and when I say a lot, I mean like trillions of words, is super important to be able to build a powerful enough base foundation model such that when you fine tune it on a data set of that size, it's actually high enough quality that you produce a model that scores highly on like sort of the automated metrics and sort of the human evaluation metrics as well. Llama 7 billion is only actually trained on, so the original Llama 7 billion was actually only trained on 1 trillion tokens. Estimated reports are like OpenAI's models. They're trained on like the order of like 10 trillion tokens. Much more data. And what's cool is that there's this really cool European AI startup called Mistral that probably most of you have heard about because they raised $100 million to build an AI model. They actually did this like 2 weeks ago. So Mistral just announced their release of a 7 billion parameter model that was trained on about 6 to 7 trillion tokens. To collect these tokens is very hard. There's actually not that many words on the internet. It's only like a couple trillion. So you have to go digging into the sources where people start yelling at you if you train on those data. For instance, like books in and out of copyright. This is why a lot of these companies don't release their actual data mixes. If they did, they would get sued into oblivion. They just pretend like they didn't train on in copyright stuff. OpenAI is probably the biggest offender, but like even Mistral, as the sort of like European open source AI company, they also didn't say what they trained on, and there's a reason for that. But what's cool is that the model's out there, it's open source, and it's competitive actually with these larger 13 billion parameter models. So if you guys, I can actually give you an example of running a 13 billion parameter model on my machine. I'll do it at the end in case my machine decides to stop working. But that's very slow. The fact that you have a 7 billion parameter model with the same capabilities as a 13 billion parameter model gives us a lot of advantages in terms of just like edge deployability and also just like general purpose utility. It also shows like we're going in a promising direction, right? I think a year ago when ChatGPT came out, it just seemed like we were so far away from and the average sort of person being able to interact with the system of this quality of this capability on their machine. It hasn't even been a year yet, and we have basically pretty good alternatives for the majority of use cases that you want to use ChatGPT for, all running locally. And that's pretty fucking impressive for for like where we are as humans. So that's really exciting, and yeah, I think that's it. So yeah, thank you so much for listening. Basically, what we care about is making AI systems more accessible, making AI systems more interpretable, and making sure that you don't have to send all your data to OpenAI. So if you want, give it a try, and happy to chat anytime afterwards. Get some Belgian beers tonight. So. And I think we have some time for questions, possibly. Please.
There was a little spike on the graph around 7 billion parameters. Something went wonky. Yeah.
Yeah, so this spike is a different type of 4-bit quantization algorithm. Essentially, in this paper, they were testing out different types of quantization algorithms. This is like, you can, for the purpose of this talk, you could ignore it. But yeah, yeah. The red line is what you care about here. This is like the thing people use nowadays. Yeah. Anyone else? Cool.
Will there be Mac GPU support also?
Uh, there is. I was actually just using it in front of you.
GPU and CPU.
This is running on the M2 integrated GPUs. Yeah, yeah, yeah. So, yeah.
Nice. Would it make sense if you have a big code repository to train on your own repository and generate from there?
You know, you don't actually want to train. What you want to do is you want to like have that in a set of documents you can retrieve over it and prompt the existing LLM for. Usually, if you have a bunch of code, what you'll do if you want to have a good code model. So, like I know Amazon was demoing their like code assistant model that they have. There's tons of actual startups right now that are doing like local code assistants. What you want to do is you want to fine tune, or rather, you want to continue pre-training the model on a large repository of code. So there's like giant GitHub dumps you can access. Maybe if you're a large enough company, you have millions of lines of code that you can train on yourself. But then what you want is in the given context that you're coding, you want to go in and prompt the large language model with the relative sort of code snippets that you think it should have access to when it's trying to, for instance, answer a question about your code or complete the next couple of tokens in your code. It doesn't actually make sense to continue training on sort of like a local code repository. What's up?
You mentioned Docker support. Where can I find more about running this in Docker?
Oh, super easy. If you want to, you literally, yeah, yeah, yeah. Well, I didn't say it. So if you just go to the repository, you'll see a cool thing called the API, which is literally just a fast API app built over top of it with Docker images. Um, yeah, so it's that easy. Cool. What's up?
So, what is a normal contact length you recommend? Like, what is the normal contact length with this?
Yeah, so It turns out that the more so context, what he's asking about context length. This is basically like how many words the model can have in its sort of current window of knowledge to be able to generate out the next word. So like how much information is it informed upon in order to be able to like give you out more generations of words. And the question he had is, what is that context like? So there's companies like Anthropic, which are like, we have an 100,000 token context length, like we're the coolest place in the world. OpenAI's models have anywhere between 8,000 to 32,000 words that you can fit in a single sort of like window to do a generation out of. These local models, most of the ones that you pull off the shelf, it's a function of the context length of the underlying foundation model. So like Llama 2 has a context length of I think about 4,000 tokens originally, but there are techniques you can use to go and extend those context lengths. The one trade-off is if you want to run it on low resource devices, what happens is that context length actually, like the more words you've given to your LLM in order to do a generation, the more memory it's going to use in actually performing that next token generation. Which means that if you have your model deployed on a super low resource device, you'll have a fundamental limit to how many tokens you can have in your context window. But if that's not your problem, there's ways to take a 2,000 token context window model and extend it out to arbitrary lengths with like with only some degradation in quality. There's like techniques for that. And it's all available. Like everything I'm saying here, the reason I didn't present you a bunch of code in this talk is like you can go in and Google all these words and find tons of links and how to find them. That's uninteresting. So, what's up?
Is there extensive developer documentation?
Yeah, you can go to docs.g. So if you go to this repository, you'll find everything you need. But there's a bunch of developer documentation. Yeah. So if you want to get more nitty gritty, you can go into the underlying sort of like C++ code we actually forked off of Llama CPP, read that, work with that. But if you want sort of like the easiest developer API, if you don't eat C code the whole day, this is one of the best places to play with it. Cool.
What are your thoughts on modular mojo?
On what?
Modular mojo?
Module?
Mojo.
Mojo. Okay, so Mojo is this Python superset language, I believe, that does accelerated computing. It's like you get all the Python syntax, but it's like it's fast as Julia. I don't know. I think they're doing a lot of great marketing as a startup building Mojo. That's what I have to say. Like anything you could do in that, you can equivalently do by writing like NumPy code. Like, yeah. But also, like, they're investing money in it, and like, good for them. What's up?
It seems that most open source models are quite targeted to English. Is there a base model that is better in handling different languages?
Yeah. So the best base models right now are in Chinese and English. Yeah. This is just where all the investment's coming in. But clearly, as you have teams of, for instance, like all French people going in and starting a startup that raises $100 million, like Mistral, to be able to go in and train these models, you'll get models that are trained on other languages. The problem is that, unfortunately, like everyone in this room, right, we all come from different corners of the world, but we're all speaking in English. Most of the text on the internet is English text. Like there's just like several order of magnitudes more English than there is of any other sort of like lower resource language. And I'm not even talking about like the super low resources like African languages. And it's like it's an open problem in NLP. Just like how do you make machine learning models trained on language as good as the ones that are trained on English language? And there's ways to like sort of cheat your way into it, like get like good performance. Like for instance, if I ask the model to write out German, I think it actually can. Let me switch to one of these larger models. This might be able to write German. This is actually a 13 billion parameter. You see how it's a little bit slower because I'm literally loading in like 8 gigabytes onto the shared VRAM of this machine right now, but it's all local. What'll happen is it can do it, but it'll be just a lot. It'll be a lot worse. There's people working that direction. It'll get there, but it's just like a fact of the internet right now is that there's more English than anything else, which biases the models to be better at English.
ChatGPT is really good.
Yeah, that it is. Do you know why? You know how much money they paid Scale AI to generate all the different languages? So like, write me a sonnet in Dutch. I can't read Dutch. Is this bullshit? Is this not? I don't know.
It's Dutch, all right?
It's definitely Dutch.